We start recording. Our next speaker is Guanlong Bao from Shantou University, who will speak on a family of Mobius invariant function spaces.
So hello everyone. So I wish everyone have a good day. I want to thank for the invitation of Professor Mazregi, and I want to thank all the organizers of the conference. Today I will talk about a family of Mobius invariant function spaces. The talk has two parts. The first part is about boundary multipliers of family of Mobius invariant function spaces Fp p-2s. So this is based on joint work with UDPOR. The part two is about intersections and unions of Fp p-2s spaces. This is a joint work with Has Wunan and Fanqin Ye. So for the proof of the both results, we will need to construct some Blaschke products. So here is some notations. It's very standard. So we denote AUTD, the Mobius group. So the sigma A is denote this map A minus Z over 1 minus A bar Z. So now we recall a general family of function spaces. So for P is positive, Q is bigger than -2, S is non-negative. Then FPQS is the set of functions F analytic in the unit disk, and such that this integral and then take super is finite. So this is known as a general family of function spaces. So it introduced by Professor Ruhan Zhao in 1996. So for this family of function spaces contains only constant functions if S plus Q is smaller or equal to -1. So this family of function spaces contains many other spaces. For example, Fp p plus Q0 is just the weighted Bogman spaces. Among FPQS spaces, if we take Q is equal to p-2, then this space is Mobius invariant. So in the sense that for every F in Fp p-2s and every phi in AUTD in the Mobius group, the seminorm of F composed by phi is equal to the seminorm of F. So this kind of space is called Mobius invariant spaces. So Fp p-2s is Mobius invariant. So so we will focus we will study this kind of Mobius invariant spaces. So of course we need a net S plus P bigger than 1. Otherwise, Fp p-2s just contains constant functions. So if S bigger than 1, then all these spaces are the same and equal to the block space. So if we tweak P is 2, then F20S is just the well-known Mobius invariant space QS. So QS space was introduced by Onazakari, Xiao, and Zhao in 1995. And then there are 2 books about QS spaces. For QS, if S is 1, then Q1 is just the space BMOA. So in fact, for this kind of family of FPQS space, so as far as I know, the theory of this space has a nice connection with the field of linear system theory and cybernetics. So where we can check this paper. So this kind of spaces has nice applications in other field. So for analytic spaces QS, then spaces has a boundary. Now we recall some QS some Q space on the unit circle. Here T is the unit circle. QST space, the definition is like this. This is a double integral on arc I, and then take a super of I is the set of the unit circle. So this is the definition of QST spaces. So it's known that if S bigger than 1, then QST space is just the BMO space. So in 1997, Essen and Shaw proved that for S is between 0 and 1, then and F is in the Hardy space H1, then F belongs to QS. If and only if F star belongs to QST. F star means the non-tangential limit of F. So now we just recall some spaces. So for function space x y, we denote by mxy the class of multipliers from x to y. That is the mxy is the set of function f such that f times g belongs to y for all g belongs to x. So if x is equal to y, we just write myx xy as mx. So for the connector space BMO, it is known that if for BMO on the unit circle, then if F is a multiplier of BMT, if and only if F is belongs to L infinity, and this formula holds. So in this formula, the log function appeared. This is related to the growth of functions in BMO space. So for analytic case, there are a similar result. F belongs to the analytic BMO space. F is the multiplier of BMOA space. Is also if and only if F is bounded, and this formula is finite. In this formula, there the log function also appear. So this is because of this because of the growth of functions in BMO. So in fact for S is 1, QS is BMO. If S bigger than 1, QS space are equal to the block space. In fact, the multiplier, the description of multiplier of the block space is also known. For S between 0 and 1, in 2000, Shaw conjectured that F is a multiplier of QS space if and only if F is bounded, and this formula holds. There plus the S is here, plus S is here. So this conjecture was proved by Ulipor and Please in 2008 in this paper. So in fact, for the description of multipairs of FP P minus 2S space also known. Was also known. So the description can be found in a paper of Paul and Ruhan Zhao. So this is about the multipairs of the analytic Q space. So in fact, for the Q space in the on the unit circle, in the same paper, Shaw also has a conjecture. He conjectures that for S is if S is between 0 and 1, then F is a multiplayer of QST space. If and only if F belong to L infinity, and this integral and then take super is finite. So in 2015, I visited Barcelona. So Professor Paul let me know this conjecture. Then we try prove it together. So we prove it in a more general cases. So we definition the space QPST. So for P bigger than 1 and S is positive. So we definition QPST by this double integral and then take super is finite. So then we found that if we take P is 2, then QPST just QS space. So in fact, this space QPST space is the boundary spaces of the FP P minus 2S space. So we have this theory. For F, if F belongs to HP, then F star belong to QPST space. If and only if F belong to FP P minus 2S space. So QPST space is the boundary space of FP P minus 2S. So we also can find some equivalent formula, equivalent condition of QPST. So B is a colors mirror description, and C condition C is a double integral on the unit circle, and then take super. So for this QPS spaces, we also know the inclusion relations between any two spaces. If P1 is small or equal to P2, then QP1ST space is a subset of QP2R space, if and only if S is small or equal to R. So if P1 bigger than P2, then QP1ST space is a subset of QP2RT space, if and only if 1 minus S over P1 is bigger than 1 minus R over P2. So then we can description multipairs between two QPST spaces. So we have this theory. If P1 is small or equal to P2, and S is small or equal to R, then F is a multiplier from QP1ST space to QP2RT space. If and only if F belongs to L infinity, and this condition hold, we denote it by A. So this is for P1 small or equal to P2. Then if P1 is bigger than P2, then if S and S small or equal to R, then we have two cases. If 1 minus S minus P1 bigger than 1 minus R over P2, then F is the multipliers from QP1 S T space to QP2 R space if and only if F is belong to L infinity and F satisfy condition A. And if 1 minus S over P1 is smaller or equal to 1 minus R over P2, then the multipliers is just 0. And if S bigger than R, then the only multipliers from QP1 S T space to QP2 R space is 0. So in fact, when we prove this theory, we have observation I wrote in the PDF. Suppose G is real valued. Let G theta be the harmonic conjugate function of G hat. Here G hat is the Poisson extension of F. Then if we net H is equal to G hat plus I G theta, then the Laplace operator G hat and then take model is equal to the H prime, the model of H prime. So use this observation. So it's easy. In fact, use this observation. It's easy for us to prove 1 and 2. In fact, if we take P1, P2 is 2 and S equal to R. So 1 is then 1 covers the conjecture of Xiong. So use this observation. We can transform between the case of analytic space and QP and QPS space on the unit circle. So it's not hard for us to prove 1 and 2. But surprise is surprise for us that is 2 prove 3 is hard. 3 is just to prove something is 0. It looks maybe easy, but in fact it's hard for us to prove this. So to prove 3, we construct some Blask product and use some limit theory. So we need, in fact, we need to for S bigger than 2R, we need to find one function in QP1ST, but not in QP2RT. Usually, for these examples, usually we want to check the necessary theorems. But for necessary theorems, we know this number. If there exists a necessary theorems G belongs to QP1ST, but not in QP2RT, then the multiplier is just 0. But this number means the case P1 minus P2 S bigger than R and 1 minus S over P1 bigger than 1 minus R over P2. If the parameters satisfies this condition, then any necessary theorems in QP1ST must in QPRT. So this method, so this number can't to prove our case of our 3. So we need to find another method to prove 3. So to handle 3, we need to construct a certain Blaschke sequence AK convergent attend to zeta in the following way: BZ, the BZ is the Blask product corresponding to AK. This such that this BZ belongs to FP1 P1 minus 2S, but it's not in FP2 P2 minus 2R. So by a paper of Professor Garina, Place and Wokertic. So this is not possible if the sequence AK converges to zeta non-tangentially. So we need to find a tangent region to construct this kind of AK. So so we consider this region for C is positive and delta is bigger than 1. We net omega delta C is the set of our point REI5 satisfies that 1 minus R bigger than C, then the model also with the sign function. So then this kind of region omega delta C theta touches T at EI theta tangentially. So we see that a function H defined in D has omega delta limit L at EI theta. If HZ tend to L, as Z tend to EI theta within omega delta C theta for every C. So this region appeared in Neger, Rudin, and Sharper's paper. So they proved that for P bigger or equal to 1 and F belong to LP, alpha is between 0 1 and H has this representation. Then if RP smaller than 1 and delta takes this parameter, then the omega delta limit of H exists almost everywhere on the unit circle. Then use this theory is usually to check that here we net BPS is the space of Bezoff type space. Then if P bigger than 1 and S smaller than T is bigger than 0 and 1, then and H belongs to BPS, then the omega 1 over T limit of H exists almost everywhere on the unit circle. So to prove this three, we will need this proposition. And we also need the description of inner functions in FPP minus 2S spaces. So this is the result of Professor Guanlong and Routier. So they proved that for S is between 0 and 1, and P is bigger than the maximum S 1 minus S. Then an inner function in every inner function in FPP minus S, if and only if it is a Blask product, whose 0 is ZK satisfies this condition. So it is worth to mention that this condition is independent of P. So then we should construct the Blask product we want. So we for R small s between 0 and 1 and T belong to 0 and 1, and for every EI theta belongs to the unit circle. We found that there is a Blask sequence AK such that EI theta is a unique accumulation point of AK, and AK is in that some region omega, and C omega 1 minus AK the sum of this sum is on S Cantor's measure, and this sum related to R is not R Cantor's. So use this result. So this construction play a key role to prove part 3. So for every yes, part 3 means that if F is a multiplier from one could be as space to another could be as a space. We must prove F is 0. So then we take for every yes theta belongs to T, then we can find AK in this region. Then by that result of by this of Nagel, Rugin, and Schaper, then the related function has omega limit. Then we can for every yes theta belongs to T, we can find this kind of AK, and the limit exists. Then we can prove the Poisson extension of the model of F is there tends to 0 for every yes theta for almost every yes theta in T. Then we can prove that the only multipliers is 0. So in fact, this to prove something is 0. So our proof is very complicated. But it's depending on this construct of Blaschke product. But we did not find some easier proof. But I believe maybe there are some easy proof, but I don't know. So in fact, for the multipliers, for the description of multipliers of the FPQS space, so this question is not commonly. So it remains open to character multipliers of FPQS space for certain range of parameters PQ and S. So one can check this paper. So this is part 1. So the proof is based on this construction. So the part 2. So the talk of my part 2 is about intersection and unions of related to FP P-2 as space. So this is a recent work, joint work with Wulang and Ye. So intersection and unions of certain analytic function space usually appears in the study of complex linear differential equations. So next I will cite two results to explain this observation. So we for F if F is analytic in the unit in the unit disk, we let sigma F the order of the group of analytic functions. Sigma F is the definition. This is the definition of sigma F. It is called the order of groups of analytic functions. So in the study of complex differential equation, mathematicians pay attention to the order of the solution of this equation. So this equation here denoted by E1, and K here K is a positive integer, and the differential AJ is analytic. So in 2009, Cohen and Rotia proved that if alpha is non-negative, then all solutions F of the equation E1 has a finite growth. That is sigma F is smaller than alpha. Then if I know if the coefficient AJ belongs to the cap, this intersection of Bowman space AP alpha. So you see, so this intersection, the intersection of certain analytic functions appeared in the study of complex differential equation. So we have another examples. So we consider the second order complex differential equation. So we denote it by E2. So here is of course A is also is analytic on the unit disk. Then in this theory there is a theory about solutions of E2 of equation have pre-given zeros. So given the theorem AK of distant points on D, one can answer whether there is a function A such that the E2 has a solution F with zeros precisely at the point AK. So in this case, AK is said to be a pre-given zero sequence. So this problem was first studied by Shantou. So a sequence AK is said to be separated if this condition holds. So in 2019, a result of Guanlong has a result said that here S is below small or equal to 1. If lambda is a separated sequence such that this measure is a S Cantor's measure, then there exists a function A such that A satisfies this condition, and the equation this equation has a non-trivial solution F, whose zero sequence is lambda, and this F can be belongs to S cap at infinity. So later my co-author Ye has strong this result. His result is that S is belong 0 and 1, but Guanlong's result is that S can take 1. Here S is belong to S is 1 belong to 0 and 1. Q is bigger than 1. Then if lambda is a sequence such that this S Cantor's measure, so the condition is the same as the theorem above. Then exists function A such that this condition is a S Cantor's measure, but this equation has a solution F in this cap of function space, and F whose zero theorem is also lambda. But if we compare this result of this result, we found that the condition is the same, but A for the condition of A, but we can find that the A is this condition is weaker because if for K bigger than 2, we have this result. So this condition is weaker, but we can get a stronger condition. So F here F is in QS, but here F is in the intersection of FP minus 2S. So you see the intersection of assumption of certain space also appeared. So anyway, in the theory of complex differential equations, usually some is the intersection or union of certain space where appear. So one can check more examples from some papers. So it's quite natural to study the inclusion relation of the intersection of unions of function space, because it appears in this in the theory of ODE. Then it is quite natural to check the inclusion relation of the intersection and the unions of analytic function spaces. So in a paper of 2005, Cohen and Rotia he proved that. So here APQ means weighted Bergman spaces. So if you take AP star Q star, you take the intersection of Q star and then take the intersection about P star. It's just equal to the here is P and then Q star. Then you take the intersection of Q star, and then it's also equal to the intersection of AP star Q. Here is the intersection about P star. So for the union, there are the similar result. So this is about weighted Bergman spaces. So for the general function spaces, there are also some result said that. So FP star Q star S, take the intersection of Q star first, and then take the intersection of P star. Then is equal to here is FP Q star S, and then take the intersection of Q star, and then is also equal to the intersection of FP star QS with P star is smaller than P. So for the union, there are some for the union there are some similar results. So also for the here is there are two intersections or two unions. If just one intersection or one union, or they also have this result. But here take both sides of this formula. Just take the intersection of P star. But if we take looks one, if looks for formula one, if the left hand is the left hand takes the intersections of parameter P, and the right hand takes the intersection of the parameter S. Then this is not equal. It's just a subset. And then for the union, the left hand for the formula two, the left hand is take the intersection related to S, and the right hand is about the union of P. So Kohanen and Ratia proved that if S star is 0 or S star is 1, then the inclusion 1 is strict. And if S star is 1, and then the inclusion 2 is also strict. So they left they posed a question that if star is between 0 and 1, how about whether the inclusion 1 or 2 are strict? So we started. Recently we started this problem, this question by constructing some plastic products. So in our construction, we need Carson type of measures called K Carson measure. So for K is increasing function, the positive increasing function on the integral 0 infinity. Mu is a non-negative Fourier measure. Then mu is called a K Carson measure if this integral and then take supreme is finite. Of course, if we take KT is T power S, then mu is K Carson measure if and only if this measure is an S Carson measure. So for the study of K Carson measure, we need this condition 3. here phi k is the supreme of this function, and then we denote by 3 this condition. We see that k is the doubling condition if has this condition, because k is increasing, so just kt of course we are smaller than k2t, and then we need this condition. If k satisfies this condition, then we see k satisfies the doubling condition. So we will need this theory. So k is for mu is the sum of Cn times delta Zn. Then mu is k current measure if and only if this condition hold. So to study that the strict inclusion relation. So we need of course we need this result about the inner function in FP minus 2S space. So in fact we mentioned mentioned before. So if an inner function in FP minus 2S, if and only if f is the product and satisfies this condition, and this condition is independent of p. So in our proof, we need to construct some good Blask sequence. So the first example is this. We net kt is for t is 0 and 1. We net kt is t power s times the ln 2 minus 2t with power full p. So then there is a sequence zk such that ei theta is the here ei theta is we given ei theta in the unit circle first. Then ei theta is we can find a sequence zk such that ei theta is the unique accumulation point of zk, and 1 minus zks delta zk is not a s kind measure. And sigma delta zk is a k kind of measure. So two in there, then we by this lemma we can find a Blask product contributing to zk. Then 2 means that b the Blask product, that Blask product is not in FP minus 2 S space. But 3 means by 3 we can get that Blask product is in the intersection of some F spaces. So this example is this. So we net I will write the zk exactly. So we set fx is equal to x with the power minus s and times e pi 4 pi times x with the power minus alpha. So here alpha is bigger or equal to s or p minus 1. So this f is a decreasing function on the interval 0 of infinity. Then we denote f minus 1, the inverse function of f. Then we can define this zk like this. Zk is equal to 1 minus k minus 1 over s times e I theta k. And we net this theta k is equal to theta plus f minus k minus 1k. So this zk will satisfies this condition 1, 2, 3. So this is one construction of Blask sequence. This construction can be used to prove some severe case of the strict inclusion 1. For 2, for the severe case of 2, we need to another example. So we net k is t power s, and times this function involves the log functions. So then we can find a sequence ak such that the given I theta is a unique accumulation point of ak, and this sum related to the parameter s is on s Carnot measure, but sigma delta ak is not a k Carnot measure. So use this construction, we can find we can find the corresponding Blaschke product, and then we can use that Blaschke product to find the strict inclusion relation related to the union of F space. So this construction like this, we net ak is equal to 1 minus k minus 1 over s, and then with a log function, and then the arc is theta k times e I theta k. Here alpha is between 1 over s and p plus 1 over s. And theta k minus theta is a sum from k to infinity from this sum. So use this lemma, use this construct of Blaschke product, and this construct of plus product. We can and then use the k Carnot measure. We can prove this result. But the intersection of fp p minus 2 s star, the intersection is about p. Here the is a proper subset of the intersection of fp star p star minus 2 s with s bigger than star, and also for the union is also is a proper inclusion relation, but we just but we did not get a full answer to Cohen and Runti's question. We did not get a full answer. We just their question is about here. There is alpha here. We just know the case of alpha is 1. For the alpha is 1, fp p minus 2s is Mobius invariant space. So we just know the special case. Special case is about the Mobius invariant spaces fp p minus 2 space s space. So that's all. So thank you for the listening.
Thank you. We have time for questions.
Hello. I have a question. Can you hear me?
Yes, please go ahead.
Yes. Hi, Professor.
Yeah, thanks, Guanlong, for interesting talk. In one of the theorems, you have characterized the function space fp minus 2s by this boundary functions that's in qpst. right?
Yeah, maybe this. Is this your mean?
Before this, the QPST space. Yeah, here. So what happens when Q is not P minus 2? Do you know? Do you have any idea? Do you have like similar or someone?
So for as far as I know, FPQS for some choice of parameters P, Q, and S, FPQS space becomes the Morris space. So in fact, for Morris spaces, there are some results about the boundary. There are equivalent description about the use boundary functions. But
for Morris space.
For some special choice of PQS, FQS space becomes is just equal to Morris space. But for Morris space, there is description why the boundary function. But as far as I know, there is no paper about the full picture of PQS why by boundary functions. So this question, so your question is very interesting, and there are no full answer in no papers.
Okay, thanks.
Oh, you are welcome.
Other questions? Right, if there aren't any questions, then let's thank our speaker again.
Thank you.
We'll see you tomorrow.